Derivatives of inverse functions. What are inverse functions? How do we define them? Why? That would be around the origin. But if you did it around the x-axis, then around the y-axis, you just now. Yes. The inverse function, let's say we had, this is the easiest one. What graph is that? What's that function? It crosses through one. Very good. It's actually a to the x, but we typically use it for e to the x for science purposes. What kind of function is that? What's the name of that? Very good. This is an exponential. The inverse of it looks like this. So this is the exponential. What's this one? It looks like it's actually a curve. Yep. The logarithmic function. And if you look at it, it's flipped across this diagonal line, y equals x. Because in algebra, how do we find inverse functions? Yeah. To find the inverse function, switch x and y. And what's the next step? Very good. Very good. Solve for y, and that y is represented as an inverse. Note, this is the most common mistake. I know I did this when I was a student. Because if you had 3 to the power negative 1, how would you write that? One over 3, right? A negative exponent typically means you just change the position. If it's on top, you put it at the bottom. If it's on the bottom, you put it on top and drop the negative. It's not the same when we deal with functions. So when we deal with inverse functions, it's not the reciprocal of it. It means that, well, how do you prove if something's an inverse or not? What's the test? George, okay, let's look at this. Here's an example. If y equals 3x plus 2, find the inverse and prove it. And prove that it's the inverse. Well, first go ahead and find it. Go ahead and find it first. So the first thing you gotta do is switch X and Y. Now you gotta solve for Y. So we subtract 2. And divide by 3. So my inverse function is x over 3 minus 2/3. Or you could just put it as x minus 2 over 3. It means the same thing. How would you graph them? Hmm? Okay. So the first one, let's say it is 3x plus 2. So yeah, let's create an XY chart. So when x is -1, when x is 0, when x is 1. Let's just keep it minimal. When x is -1, what do we get? Yeah, -1, because it's 3 times -1 plus 2 is -1. So at -1, it's -1. When x is 0, what's y? 2. It's when x is 0, y is 2. When x is 1, y is 5. So we know it's linear equation, so it's like this. To graph the inverse function, just switch x and y. So when x is -1, y is -1. When x is 2, y is 0. When x is 5, y is 1. Because remember, to graph it, how to find it, you have to switch x and y, which is all it really does, is you switch x and y to find the points of the inverse. So at -1, it's -1. At 2, it's 0. At 5, it's 1. So as we can see, it's symmetric about the line y equals x. That's all there is to it. Let's look at even more complex on a curve now instead of a linear equation. Because we can adjust the domain to whatever we need it to be. Find the inverse and then graph the two functions. That's you. All right. So let's first find the inverse. So we started off with this function. So we switch x and y, solve for y. Take the square root of both sides. So we have to put a plus or minus here. So the inverse of y equals plus or minus the square root of x. But since our domain is restricted to only positive x's, We only deal with the positive x's. Here's x, here's y, and here's inverse. At 0, 1, 2, 3. 0 squared is 0. 1 squared is 1. 2 squared is 4. And 3 squared is 9. So the graph looks like this. It's half a parabola. The inverse is a radical. What does the radical look like? What's the graph? Right. So it starts at 0. It's 0. At 1, it's 1. At 4, it's 2. At 9, it's 3. Looks like this. Again, if you remember what the graphs look like of the library of functions, we know what the answer is supposed to look like. Again, it's symmetric about the line y equals x. So if you notice here is 0, 0. So all we do is switch x and y. So the y becomes the x, and the x becomes the y. The y becomes the x becomes the y. So at 4, the answer is 2. 9, the answer is 3. So that's the easy way of doing it. So let's go back to the original one we just did. 3x plus 2. And that one was, it was x minus 2 over 3. Let's take the derivatives now. Take the derivatives of both of these. And we'll see something pretty unique here. So what's the derivative of the first function? What's the derivative of the second function? Hmm? because here we have x over 3 minus 2 over 3. This is the same as 1/3 x minus 2/3. The derivative constants go to 0. The x disappears, so all we have left is the slope. Y equals mx plus b. So what do you notice about the slopes? Okay, let's look at the second one we did. Find me the derivatives of those. Derivative of the first one is what? 2x, that's an easy one. Now this other one, so it's 1/2 subtract 1. So it's 1 over 2 x to the power 1/2, which is 1 over 2 square root of x. So what do we notice about these slopes? Remember, the first derivative finds what? The first derivative finds the slope of a curve at a given point. So the slope of this one is 2x. This one is 1 over 2 radical x. This one is 3. This one's 1 over 3. So what do we notice about the functions? They're reciprocals. So if the slope of this one was a, or m, then the slope of this one would be 1 over m. Which means what? Remember, this is the inverse. What is m? M is f of a. So again, it's the slope, so it's a derivative actually. So what we're getting to is we're defining what these functions are. So if we were to put this, our formula that we'll use is this. The derivative of an inverse is equal to 1 over the derivative of f of a. Let me show you what this stuff means. We have a point here. That's a. It corresponds to a b value. So this is the point AB. The slope of that curve is that. Oops. Which is equal to the derivative. So far, so good? So what's the inverse going to look like? Of this one, we just did that. It's the... So now, since we use the points A, B here, what points do we have here at this point? This is B, and that's A. Because remember, you switch X and Y for your inverse. So the derivative at this point There's a slope. This is the same as since they're reciprocals, that's the same slope as that one. So far, so good. Now, what's another way we can write this? What is f prime of a? Remember, we want it to be with respect to b. We want it to be with respect to b. So what do we know about it? We know since this is a derivative, it has to be a derivative. And the slope of the curve is so this is the formula that we'll be using from now on whenever look for slopes of inverses or derivatives of inverses. Which on your sheet is what theorem 3 states. The derivative rule for inverses. Oops. So if you look at your sheet, it says what? If f has an interval I on a domain AB, and f prime of x exists everywhere pretty much, and is never zero. Why is that important? Why is this part and is never zero? Why is that important? F prime exists and is never zero. What does f prime define? Slope. When the slope is zero, what does that define? A vertex. And that tells us really nothing. It's a horizontal line. We don't want horizontal or vertical lines. So we want either to be an increasing or decreasing function. So it exists and is never zero. That means it's the continuous function is either an increasing function or a decreasing function forever, or in that interval. So the range of f of x is also defined on the interval. In other words, you cannot have any asymptotes because if you have it, you can't cross that at the x value. So we have to keep that. So the inverse, the value of the inverse of x, this is the slope of the inverse. At any point B on the domain, on the interval of I. The range of the value of any point on I is the reciprocal of the value of the slope of the function f. Or it's f prime of x at b. And that says that the derivative of the inverse is equal to the point A. So let's put the formula together. Because it has to be a continuous function. In other words, it's differential everywhere. It has to be on an interval that all the x exists, so all the y exists. There's no vertical, no horizontal lines. Why is that important? Because if it's a vertical line, what's the slope? What's the slope? Undefined. We can't do anything with undefined. If it's horizontal, the slope is 0. Again, tells us nothing. So the derivative of the inverse is equal to the reciprocal of the derivative of the function A. Well, yeah, because A is equal to that point. Let's take example 1, I believe. Example 1. The function f of x equals x squared, where x is greater than 0, and its inverse have derivatives. F prime is 2x. So we just worked that out a second ago. Now, we never did verify. Remember in algebra, how do we prove that inverse exists? In algebra, what does that mean? Yes. It's what's it called? What kind of function is it? Very good. It's a composite function. So what this means is you have this is the input of that. And then conversely, both of these, you have to test both of them just in case. And the answer has to be X. That means that that's how you prove that an inverse exists. And of course, there's the horizontal line test. And it has to be 1-to-1. So let's look at the example we had earlier real quick. 3x plus 2, x minus 2 over 3. Those that's our inverse, not in derivative. So the FOF, the f of the inverse of f, what that means is this equation goes in place of x in the f function. So it's 3 times x minus 2 over 3 plus 2. Work that out. The 3's cancel. X minus 2 plus 2. The 2's cancel. It equals x. And then we just do the opposite. That means this function goes in place of x in the outer one. So whatever's in the inner goes in, so whatever's in the inside goes in place of x in the outer. So 3x plus 2 goes in that one. That's the x minus 2 over 3. The 2's cancel. The 3's cancel. We have x. So those are legitimate inverses. You have to make sure you have an inverse first before you go any further. Because if your function doesn't have an inverse, that means you may have a derivative equals 0, or maybe a vertical, or something else that doesn't exist. So this is the algebra part that we have to make sure exists. So let's use our formula. For our example 1. Where f of x is x squared, and f inverse is the square root of x. So let's plug in all our values inside there. I know, and I'm glad I just saw what I saw, is you guys looking at this and trying to understand what this is trying to tell you. That's what you have to do with this stuff. So what's the first thing? What is this part here telling me? I think the derivative of the inverse. So what is the derivative of the inverse? So the inverse is square root of x. The derivative of it is 1 over 2 square root of x. That's the left side. That's what this left side is telling us. Is that. Now we have to prove it by doing this part now. So what is this part telling us? What this part's telling us what is f prime? So this thing says it's 2. Now, in place of x, I have the inverse of b. What is the inverse of b? Or the inverse of f at b? That's that. So instead of doing this whole process here, we just have to do 2 steps and we're done. So again, if it said if x equals 9, then what we have here is 1/2 square root of 9. Square root of 9 is 3. So what does this number tell us? Remember, look at the formula. What does that number tell us? Hmm? Where did this equation come from? It came from here. Well, what does this thing mean? Well, it means this. It's the derivative of the inverse. So the derivative of the inverse, or more so, the slope of the inverse at when x is 9 equals 1/6. That's what it tells us. So if that's the derivative of the inverse, the slope of the inverse, I can put it right that way. What's the slope of the regular function? 6. It's reciprocal of it. So, but this formula, our theorem 3, is instead of going through the whole process and figuring everything out, we just do the composite function. The derivative of the outside, whatever the x is, put your inverse function in, and you're done. That's what it's telling us. See if there's another example here. Example 2. Let f of x equal x cubed minus 2 for all x's greater than 0. Find the value of the derivative of the inverse at x equals 6. Now, it's even telling us at f of 2. Because remember, this is the x equals 6 is the inverse. I think the inverse at 6 is the same thing as in our original equation. If x is 2, it equals 6. 2 cubed is 8, minus 2 is 6. Without finding the formula for what does that mean? Without finding the formula of the inverse. So all I'm giving you is the original function. And I'm telling you the slope of the inverse function at when x is 6. Well, the slope is 6 when x is 2 in that case. So what it's telling you to do is use the formula we just talked about. Find what's another way of writing this? That means the same thing at whatever b value we have. So our formula, our theorem 3 says what? What is that equal to? F prime of So it says work this out, work this thing out, because earlier we found the derivative, then took the derivative, I mean, we found the inverse, then took the derivative of the inverse. Now we're only going to use the formula. We're not going to find anything else. How do we do that? What do we need to find? We first have to find the derivative of x. We have to find the outside. So the original function is x cubed minus 2. So this is 3x squared. So it's 1 over 3 in place of x. I have my inverse. Now comes the hard part. What does this value become? We have this information. F of 2 equals 6. This is the same thing as f of x equals y. Remember our graph? What did A and B represent? A and B. So the y value is B and the x value is A. So this is really f of A equals B. So that means B is 6. But the inverse of 6 is 2. Because that's where you have to understand what the inverse means. This is our function here. Our inverse is switch x and y. So what we have here is 1 over 3, the inverse of 6. What is the inverse of 6? It's 2. You switch x and y. So that becomes 1 over 3 times 4, makes it 1 over 12. Again, it's trying to get you away from finding the inverse. Just what you're given. Let's use what you have. This is your A, this is your B. So when I do the inverse, I gotta switch x and y. All right, let's look at logarithms. Any questions so far? Derivative of the natural log function. Because remember, our formula says f of the inverse of b equals the 1 over f prime. So our original function would be the exponential function, e of x, e to the power x. The derivative, or the inverse of it is what? Or it's actually log base e of x, which is written that way. So let's look at our formula we had here. We had the inverse, the derivative of it. Yeah, only using x's. So what's our derivative? What's f prime? If this is f of x, what's f prime? Yeah, eu du. E to the power x times the derivative of x is 1. So that's e to the power x. But my x value is the inverse function. What is my inverse function? Yeah, it's the ln. So what I have here is 1 over e to the power ln x. What is e to the power ln x? Yeah, because if the base is the same base as the exponent, they cancel out. So a log base a of x equals x. Where's an example? Now, what if we had EU du type equation? So if we would have done the same thing, so we have the derivative of ln u. What's the derivative of ln? So that's du over u. What's the next example? Oh, there it is. Now let's apply this to an example. The next one on your sheet. Any questions so far? It's again, it helps if you color code your notes so you see these shortcut formulas. Just those things, not the whole thing, just look all the formulas that we talk about. That's all we're using in these examples. Example 3. Use equation 2, find the derivatives. A d dx of ln 2x equation 2 with u equals x squared plus 3 So the first one. So we have what is that one? What do we do there? The derivative of ln 2x. Well, yes, we're going to use the ln u, which is 1 over u du dx. So the derivative of this, here's the u. So it's 1 over 2x times what? What's du? 2. So 2's cancel, we get 1 over x. So what we're looking at here is the ln of x squared plus 3. We're still doing the ln u part. So the derivative of ln x squared plus 3 equals what? So here we have ln u. The derivative of ln u is what? The derivative of ln u is du over u. So what's u is this? What is du? Two x. So we have 2x over x squared plus 3. And that's as far as we can go. And the last one, u is the absolute value of x. Find that formula. So what's our u? What's the derivative of u? If everybody remember that. So what's the first part? What's the 1 over u part? 1 over absolute value of x. That's 1 over u. Times du. What is du? Remember we did that derivative about a week and a half ago. Well, before spring break. 2.5 weeks ago then. To do that, we had to define the absolute value of x as x squared, the square root of x squared. Remember what that was? And no, you can't do this either. You can't do that. You have to treat them both separately. So you have to use a chain rule, which will give you what? Times the derivative of the inside. So the twos cancel. So we have x on top, square root of x squared on the bottom. What is square root of x squared? We define that as absolute value of x. So it's x over absolute value of x. That's the hardest part. Well, actually, add it to the list of hardest parts. Whenever you try and take the derivative of absolute value, you cannot simplify like you normally would algebraically. You got to use a chain rule to figure out what the derivative is. We defined it as square root of x. So what we have here, we have 1 over 2 x squared to the negative 1/2 times 2x. The 2's cancel. So we just have x on top and this on the bottom. Now what happens? The reason we have absolute values in the x's is because we cannot have negative answers. Absolute value of x times absolute value of x is absolute value of x squared. Well, that's the same as x squared because if it's squared, it can't be negative. So they both have, so it's 1 over x. Because absolute value of x times absolute value of x is absolute value of x squared. It can't be negative anymore, so I could drop the absolute values. And then there's a definition of ln x. The derivative of ln x is 1 over x. So what this shows us, the derivative of ln x dx is 1 over x. And even more so, the derivative of ln u is du over u. So whenever you're taking derivatives of log functions, natural logs, we'll just use these formulas instead. Example 4. A line with slope m passes through the origin. And is tangent to the graph of y equals ln x. What is the value of m? We have to first understand what it's asking before we go any further, before we do anything. So what is this thing telling us? Draw a picture first. If you understood it, if you understand what it's saying, you can draw a picture. If you can't draw a picture of it, then you have to go back and re-understand what it's trying to tell you. A line with slope m passes through the origin. So there's the origin. A line with slope m passes and is tangent to the graph of ln x. What does the graph of ln x look like? It's not two sides. Because what do we know about ln x? What can we not have in there? Bless you. X cannot be negative or zero. The graph looks like this. So your inputs cannot be zero or negative. All right. And it's a line is going through the origin and is tangent to the curve at one point. So all we know is at some point A, it's in there. And the B is at ln A. That's all we know. So how do we find the value of m? So what is m looking for? What is m defining? Slope. So what do we have? And what, once you know what you have, it'll help you decide what method you're going to use. Well, what two things do we know for sure? We know this point. What's the location there? So we have a point. We also have this point. So we have 2 points. We're looking for the slope of the line. This is m. How do we figure that out? Back to the basics in algebra. The first chapter in algebra. What's the formula for slope? Yeah. So if you have 2 points, go back to the basics. So this is x1, y1. This is x2, y2. So y2 is what? Y2 is ln A. Y1 is 0. X2 is A. X1 is 0. Now what? Do we know anything else? So what's the slope? How can we figure that out? So we know that what do you do next? Multiply both sides by A. So ln A is equal to 1. We're solving for A. How do we solve for A? What is ln? So we can do it 2 ways algebraically. I can convert this to ln, log base e, then bring the log over here, the conversion, algebraic conversion, which is a is equal to e to the power a, so a is equal to e. Or at this point, since I know my base is e, I can take both of those to raise it as to power e. So the ln and the e cancel. Or it's e to the power 1. So a is equal to e. Since a equals to e, that's my slope. Okay, so to the next example or next topic. Yeah. Again, it's just plug and play pretty much. Now let's look at derivatives of a to the power u and log base a of u. Hmm. You notice last discussion was ln, log base e. Now we're doing any general. A could be anything. So let's look at the derivative. The derivative of AU with respect to X. Okay. We can redefine A to the power U with respect to our exponential function, E. This is a true statement? Yeah, because it's E base ln log base E. So those cancel. So AU equals AU. So now we can go from there. Can A be negative? No, because when we deal with the exponential functions, A has to be positive. It can't be 0, can't be 1, because if it's 1, it's a horizontal line. So all we're going to do is strict this to being positive. If it's 1, it's easy for us. The reason it can't be negative, if it does, it's an oscillating function. A positive, if A is negative and -2 to the power 1 is -2, -2 to the power 2 is +4, and it alternates positive, negative, positive, negative, positive, negative. So that's the reason A cannot be negative. It doesn't have a solution there. So now, since we have this, what is our derivative of that equation? How do we take the derivative of this? Since we have this equality, what's the derivative of this? How do we take the derivative of E? So the derivative of E to the power U is what? EU du. So our U is that. So what's the derivative of ln AU? Well, also, since this is an exponent, it can go out in front. By the exponential rules. So we're next. So EU du would be e to the power ln a to the u times we'll take it again. So that's the exponent there. This one, derivative of u is dx. So it's where ln a is a constant. So the derivative here would be EU du. which would be e to the power ln au times ln a. That's du. Or u. So what does that become? Yes. What's that? It's still there. So what does that become? But if you think about it, also, if we divide that, the du over u is ln a, if we integrate it. So what do we go from there? Remember, e to the u is eu du. That's what you did there. So in our example, u is ln a to the power u. The derivative of u is du ln a. Oh yeah, that's right. Because whatever the du is u ln a. So whatever u was, in this case, u is what? It's not defined. It's simply u. So what's our formula from there? How do these relate? What is e ln au? It's au. This u disappeared because it's a constant. The derivative of u is simply ln a. It goes to 1. So there's our derivative. So the derivative of any base a to the power u, some equation of x, this is the derivative of it. Let's put that in an example. A, the derivative of 3x. Using this shortcut here, what's our answer? Remember, we're looking at the derivative of a to the power u dx is equal to au ln a. Because remember, the A is what's on the bottom, so it's ln A. dx 3 to the power negative x. What's that? Well, since the exponent here is negative, it's going to be the same, pretty much. So we'll have 3 negative x ln 3, but negative, because the derivative of the exponent is -1. Three sine x. Actually, because remember up here we only really used x. So we have our formula for AU ln A du. That's the whole true formula. So our solution is 3 sine x, that's AU, ln A, which is ln 3. What's du? What is u? Sine. So du would be, there's your answer. So far, so good. Again, it's just what once you understand how to apply things in these formulas, it's just plug and play. But up until now, we've dealt with EU, ln U, or ln E. What if we had log base 5 of x? How would you do that? Right. How do we do that? Use change the base formula. The change of base formula says this: log A of x equals ln x over ln A. Whatever the equation is, and whatever the base is, goes on the bottom. But we're making them both with respect to ln. Because all of our equations, all our derivatives are with ln so far. So for this one, What would our change of base be? Ln x over ln 5. Now take a derivative of that. Now we take a derivative of this. The beautiful thing is, what's ln 5? It's a constant, so I can just bring that out in front and not worry about it. Now all I got to do is take the derivative of ln x. What's the derivative of ln x? Yeah. So it's 1 over ln 5 times the derivative of that is 1 over x. Remember, the derivative of ln u is du over u. So the derivative would be 1 over x ln 5. So in general, if we had log base a of u, the derivative of it would be what? You can compare it to this one. Where did this number come from? It's whatever that is. So we're going to have on the bottom, we're going to have u. That's the operation. Ln a. And what else? We have to take a derivative of our u. Remember, the derivative of the logs would be du over u divided by the change of base. Where's that? So this is the formula for any log. Well, yeah, we just everything we've done so far was with E. This is only now if it's not E. Yeah, because if you think of it's easier if you just use the regular formula for DE. The log or ln u is du over u. It's much easier. We don't have to worry about the 1 over a, 1 over whatever part. But yeah, you can do it. A lot of stuff will cancel at the end. Logarithmic differentiation. Example 6. This one's going to be find dy dx if y is equal to x squared plus 1, x plus 3 to the power of 1/2 over x minus 1, where x has to be bigger than 1. The clue is in the title. So what can we do here? Again, this goes back to the rules of algebra. We could use the quotient and the product rule and just spend the next day or so working that out. Or we can simplify it. If we take the ln of both sides, what good would that be for us? Well, the ln's, what's the rule for this part of the ln? We can now split these up. If it's multiplied together, then I add them. If it's on the bottom, I subtract it. So now we're doing implicit differentiation. Let's find the derivative now of these. It's a lot easier. What's the derivative of ln y? Remember, the derivative of ln u is du over u. It'd be 1 over y. What else? Remember, y is a function of x. dy dx. Right. Whenever you take a derivative of y, you have to put the dy dx after behind it, because y is a function of x. What's the derivative of this one? This goes on the bottom, and the derivative of this goes on top. The constant goes in front. So the x plus 3 goes on the bottom. The derivative of x plus 3 is 1. It goes on top. Derivative of x minus 1 is 1. Anything difficult so far? Now what do you do? Get rid of the parentheses. X squared plus 1, 2x. So it's 2x plus 6. Actually, we just leave it out in front. So 2 times x plus 3 minus 1, x minus 1. Why is that important? Because if we were conscientious, we have the common denominators and everything. But That's a whole nother story. We're solving for dy dx, right? How do we get rid of this? Hmm? It's already divided. Multiply both sides by y. So dy dx is equal to y 2x x squared plus 1 plus 1 over 2 times x plus 3 minus 1 x minus 1. What is y? Y is this. X squared plus 1 x plus 3 to the power 1/2 x minus 1 times what we have. And there you have it. That's dy dx. You see how big of a pain it'd be if we multiply this thing out and everything. Yes and no. Yes, I do like this because think of the work you'd have to do next. You'd have to first get a common denominator here, or even save time. You just multiply these out. These would cancel. That would cancel. So we have other things that would cancel, but we still have to find common denominator and then combine them all, which would be very painful. So for this, I would leave it as is. Worst case now, always try, once you get this far, try it as an answer. If it says needs to be simplified, then get a cup of coffee and get ready to stay there for a while. All right, let's see what else. Oh, example 7. Oop, I'm sorry, you got it. Again, is this difficult? No, it's just a lot of writing. It's a lot of writing. Example 7. What's this? Oh, irrational exponents. Okay, that explains it. Differentiate f of x equals x to the power x, where x is greater than 0. X to the power x. How do we do that? What did we do last time in the last question? Yeah, we took it to the base c. We laid it to base c because now we have this. So what do we have? We have so I could define x to the power x. We could define that as what? E to the x, x to the x. That would be the same as e to the x ln x. Multiplied. E to the x ln x. That's the same thing. If you think about it, remember, what do you do with a coefficient? It becomes a power. E and ln are the same, so they cancel, so it's x to the x. So my whole thing is we're going to raise it to power e, so we have to make this exponent in terms of ln. So we have to work backwards from what we know so far. So we know that we can rewrite our equation as e x ln x. Because now we can take the derivative. So it's EU du. So we have E x ln x. U is x ln x. So the derivative, we got to use the product rule. X ln x. The derivative of x is 1. The derivative of ln x is 1 over x. Ln x plus 1. X times 1 over x becomes 1. And there's your derivative. Everybody see where I got all this stuff? Like, so this is my EU. That's my EU. So this is F and this is G. So F, G, F prime, G prime. Since it's a product, I multiply and add. Ln x times 1 is ln x plus x times 1 over x. The x's cancel. So we just have 1. So that's EU du. And that should be it. It's a lot of work. But again, you have the formulas there. Once you could, this is the hardest part. I'm not going to lie to you. This was the hardest part here. Converting it to an ln function. So once you raise it to e, what can you do? How can you rewrite this so it gives you the same equation? You're not changing it, you're just changing the way it looks. That's the hardest part. But once you get it down, it's, I mean, once you define that, it's a matter of EU du and you're done. Which is why we want it to be log base e. All right. I think as far as we wanted to, but oh well.